Welcome. In this video I'm going to talk about factors that can affect your reaction rate. Now when we talk about affecting the rate, most people assume you want to speed up the reaction rate, but that's not always true. Sometimes you want to slow down the rate. Some examples of that would be, like in the case of food, you want to slow down how quickly it spoils or goes bad. And sometimes with diseases, we can't necessarily speed up or we can't necessarily stop the disease, so instead we want to slow down the progression of the disease. So affecting the reaction rate can be to make it faster or slower. So the first one is something that your book calls the nature of the reactants. And that simply depends on how reactive the elements are. More reactive elements are going to have a faster reaction rate because they more easily or with less energy can gain or lose electrons. So remember, 1A and 7A elements are the most reactive in the metal and the non-metal groups, whereas the noble gases are going to be the least reactive. So if you're designing an experiment and you want high reactivity, you might select something from the 1A or 7A families. But if you want low reactivity, like they do in light bulbs, then they use noble gases or a mixture of noble gases in there. The second one is concentration. And concentration often gets mixed up with volume. Concentration and volume are not the same thing. Concentration is more particles in the same space. So you haven't changed the volume, you've just put more things in the same volume. So more particles in the same space is like a more crowded hallway, and the chances of collisions go up. And when you have more collisions, you have a faster reaction rate. If you wanted to slow it down, then you could decrease the concentration. Surface area, this is similar to solutions, that if you expose more particles, if one of your reactants is a solid and you increase the surface area, then the other reactant is more likely to collide with it. And again, more collisions means a faster reaction rate. If you want to slow it down, then you decrease the surface area. You put it, into some kind of a compacted form instead of spreading it out. And I've used the analogy of dodgeball. This is like your team huddling together in a circle so the interior people are safe, or spreading out in a line. Number 4 is temperature. An increase in temperature is going to increase your collisions, and it's going to increase the energy of each collision. So temperature really has an effect on reaction rate. And again, you can either increase temperature to speed it up or decrease temperature to slow it down. But because it both increases the number of collisions and the energy of the collisions, it is estimated that every 10 degrees doubles your reaction rate. Activation energy is another way to affect the reaction rate. We talked about activation energy in the first section from chapter 16, and it's the minimum amount of energy needed when the reactants collide to form the product. So it's like throwing your dart at the dartboard. It has to have enough energy to actually pierce the dartboard and stick to it. It's abbreviated EA, and if you have a higher activation energy, then the chances of the product forming is going to be less, and the reaction rate will tend to be slower. But if the activation energy is lower, then the chances of forming product is going to be greater and your rate will tend to be faster. All reactions have an activation energy, whether it's endothermic or exothermic. And in fact, when I've drawn the graphs before, if I minimize this a little bit, when we look at a graph and we show the reactants and then the transition state and then the products, this is an exothermic graph with my reactants and products, whereas this would be an endothermic graph showing my reactants and products, with the difference being how much potential energy is in the reactants and products. In both graphs, what I'm showing is here's the activation energy. Here's how much energy the reactants need to form that product. So the lower this amount is, the faster the reaction rate will be. And in my case, I drew it that the endothermic reaction has a higher activation energy, but it could have a lower activation energy. This reaction could just as easily have been something like this and still drop down to here, and now it's got a much greater activation energy, and it's still exothermic. So that's what my graph here is going to look at. When you look at this graph, you should be able to identify several things on it. First of all, you should realize that this is the activation energy right here, is the activation energy for the forward reaction. And as we get into chapter 17 and talk about equilibrium, we are going to talk about the fact that reactions can often run in the reverse direction, and that here would be the activation energy for the reverse reaction when you're going the other way. So you can either read an equation from left to right in the forward reaction, or you can read it from right to left and be looking at the reverse reaction. So this graph shows the activation energy for both the forward and the reverse reaction, and each one's labeled there. The other things you should be aware of is that what's happening during that period is on the forward reaction, this energy is being used to break bonds and get things to this transition state up here. And over here then on the forward reaction, this is where the bond making or the forming of products is taking place. And again, this shows me the products have more energy, so energy was net in or endothermic. If we graph, this one is showing an exothermic because the products have less energy or more stable. And so now my activation energy for my forward reaction, again, is this same space here. How big is the hill? And here's my activation energy for the reverse reaction. And again, this is where the bond making is taking place and the bond breaking is taking place over here. And up here, this is my intermediate area where activated complexes and intermediates form. So why do I mention that? Well, because with the first factors we were talking about changing the number of collisions. But you can also change the activation energy. A catalyst and an inhibitor change the reaction rate by changing the activation energy. What a catalyst does is it lowers the activation energy. So it's like it brings that hill down, and it's like if you were doing the high jump and you were trying to get over the bar, if we brought the bar lower, more people would clear the bar. So what a catalyst, by bringing the activation energy down or by letting people move closer to the dartboard, more collisions are successful. And catalysts are critical in our bodies, as we have catalysts in our bodies called enzymes, which speed up hundreds of reactions, or our cells would die off before these reactions could take place. Inhibitors, on the other hand, do just the opposite. They decrease the reaction rate or inhibit it by increasing the activation energy or blocking the reaction, so even fewer collisions will be successful. So it's like moving you further away from the target. And this is what we use in preservatives in food to help increase the shelf life. And then just briefly, there's this idea of homogeneous and heterogeneous catalysts. And all that means is that a homogeneous catalyst is in the same state of matter as the reaction it's catalyzing. So if you have two gases reacting and you use a gas as the catalyst, it's a homogeneous catalyst. If you have two liquids reacting and you use a gas as the catalyst, then it's a heterogeneous catalyst. That's all it's referring to.